Hello, in this section we will be talking about predicate logic. So let's see an example. All flowers are plants, sunflower is a flower, therefore sunflower is a plant. So if we let P of x represent x as a flower, A is the constant symbol that represents exactly sunflower, and Q of x means x is a plant. So now this argument, all flowers are plants, for anything, if it is the P of x, if it is a flower, then it is a plant. Sunflower is a flower, and P of A, P means flower, and A is specifically sunflower. And therefore, this is a conclusion, sunflower is a plant, meaning QA. QA, A is sunflower and Q is a plant. So how do we prove this argument? So now here is the sentences here, this argument in a symbol, but now we can test for tautology by constructing the truth table, and that's what we did in the past. But here there is no corresponding mechanical means to test for validity. Is this argument valid or not? We don't have a table or an algorithm to test for this. So we must depend on a system of derivation rules to prove that Q follow from P. So once again, we're going to use the system of derivation rules to build the proof sequence leading from the hypothesis to conclusion. Two rules to strip the quantifier and another two to reinforce the quantifier. So the basic approach to proving this argument, strip off quantifier, manipulate the well-formed formula, that means using inference rule or the equivalence rule, the Morgan, and so on, and then at the end you reinsert the quantifier. So these 2 and 2 or 4 rules are here. So this is right here, you strip off the quantifier, so for all that exist. And here, once you do your manipulation of well-formed formula, you're going to reinsert the quantifier. So, and there is some restriction, but I'm going to go over them as we see specific example. Reading them now or going over them doesn't make much sense. So, strip the quantifier, we're going to call it universal instantiation. And instantiation is the process of deriving an individual statement from a general one by replacing a variable with a name. So that's what we do here. Sometimes we replace variable with a name. And UG or universal generalization is when you make it back, you reinsert the quantifier, you go back to what we had. Let's see this example again. So what we have hypothesis here and here, and this is our goal, right? So number one, I'm going to say for all x, P of x implies Q of x. That's our hypothesis. So now what did we say? What else we have as a hypothesis? P of A. Another hypothesis. Okay. Now, if I take one, and I strip this quantifier for all because it tells me for any x, anything in the domain, anything in the word, P of x implies to Q of x. So, okay. So I could say that specific x, maybe I could give it an example, would be A, like sunflower. P of A implies Q of A. So what I did, I took one and I did UI, universal instantiation. I stripped the quantifier now. So number 4 in the sequence, now what can we see? Now we go back those inference rules that we've seen in the previous section. Since P of A is true and P of A implies Q of A is also true, so I could say what? I could say that Q of A is true. Based on what? 2, 3, and P. Okay? Modest polyms, so MP here. And that is my goal here. I'm done. This is the goal. Okay? So in this case, I didn't have because they said just go, this is the goal, we didn't have to insert the quantifier. Okay? So it's less steps. So let's see another example. Now this example, the proof sequence is given, we just need to write down some justifications. So here is what I have. There exists x p of x implies q of x, implies for all x p of x, implies there exists x q of x. So here is what I could do. I should rewrite it because I'm using the deduction method which we proved in the past. This implies can be and we proved this before. And then where we have for all x, p of x implies there exists x q of x. So here where we have is, this is the goal. This is my last step. Okay? So I see that I have hypotheses, so which that's why they are written here. So this is the first hypothesis. Okay? But, and now I'm going to go back to those example I went over here. These restrictions right here. So if you have there exists p of x, you must first must be the first rule used that introduce a. If you have there for all, it's okay later to do it later. So since I have there exists, so there exists some x. Well, right away in the sequence I will call it that x, I call it a. Okay, so there exists x, I call it p of a. So now what I use is one EI, existential instantiation. EI, so I strip the quantifier, but what I said, because there exists come first, give it that variable that existed first. Set the variable like right there. The next, and then I'm going to write the second one. What I have is a hypothesis for all x p of x. So, okay. So if it's true for any x, maybe it's true. I call it p of a. That specific x is p of a. So what I'm doing here, I'm taking 3 and I'm doing universal instantiation. I stripped this and I made it this, and I stripped this and I made this. And both of them from hypotheses. Now I stop and think. Now we need to use manipulation using inference. So how do we get to q of a? Since we have p of a, and p of a implies q of a, therefore q of a is true. And where I see 2, 4, and p. Because that's my goal. I need to get to there exists some x. Well, that x, if there exists, it's a. And then you insert the quantifier, and when you insert back the quantifier, we call it EG, existential generalization. So you take 5 and you insert back the quantifier. And this is how we do this proof sequence. So let's see another argument. So what we have? For all x p of x implies q of x, and qy naught implies py naught. So again, I'm going to write down the hypothesis. So number 1, I have for all x as a hypothesis. Number 2, so I don't have there exists, so I'm going to right away set this variable as y. So I could say py implies qy. And so what I'm doing, I'm taking 1 and using universal instantiation. And I have another hypothesis, which is qy naught. And now what can we say? I have qy naught, and p of y implies qy. This looks like MT, modus tollens. So what can we get into now? So we could say py naught. Review MT, so 2, 3, MT. Okay, and that's our goal. Very simple, this one. That's the goal. Another example that is simple will be prove the argument for all x p of x implies for all x p of x or q of x. Okay, so we write down the hypothesis first. And now I'm gonna say, well, it's true for any x, therefore p of x, any x. And what I did, I do universal instantiation. I instantiate, set a variable for p. Call it x in this case, because what I'm looking at my goal to reach here, I don't see another variable, it's just for all x. Keep it as x. Now what do we know? All of a sudden I have p of x or q of x. Well, we do have a rule there where we call it p of x or q of x. In our rules, if you look at the table, I say to addition, right? So if you just, because if p of x is true, p of x or anything will be true, because an or, not and. So the next thing, again, here is my goal. Since p of x or all of x, for any x, I didn't make it any specific variable, I could insert back the quantifier. It will be for all x p of x or q of x. So what I'm doing, I'm taking 3 and I'm using universal generalization. In the reinsert the quantifier again. So again, very simple. Take the hypothesis, either you're gonna remove the quantifiers and strip them, and then do manipulation, and then insert back the quantifier if needed. So let's see this example. Prove for all p of x implies there exists p of x. And it's very common. If it is true for every x, it must be true for one x, right? Very simple. So we have the hypothesis as for all x, p of x. Now, I could use one universal instantiation. Strip the quantifier, then it will be p of x. Then back 3, reinsert the there exists, which is basically, I take 2 and I do existential generalization. Instantiation is when you strip the quantifier, generalization when you put back the quantifiers. So either universal if you have for all, or existential if you have there exist. Okay, let's see another one. For all p of x and there exists p of x naught implies there exists x q of x. How would we prove this? So we have hypothesis and another one here. Number 1, for all x p of x, that's a hypothesis. Number 2, there exists x p of x, another hypothesis. There exists x, not p of x, a hypothesis. Now, because there exists, we're going to set this specific variable first. That will be our third step. So maybe I'll call it p of a naught. So since there exists some variable that make p, whatever argument for p, not true, that means that variable should be a. And what I did, I took 2. So an existential instantiation. E for existential, when you strip it, is instantiation. Okay, now my goal is to get to QA. Okay, now my first hypothesis for all x p of x, now maybe this x can be a. So what I could say is for p of a is true. So what I did, I took 1 and I did universal instantiation. Okay, so what I end up with, PA is true, PA not is true. Well, we do have inconsistency in our proof sequence inference rules. So what we have, we know that P and not P implies Q. And this one we call it the inconsistency. If you look at the previous section, and we write it as inconsistent. P or not P implies anything, because this is false, right? And false implies true will be true. False implies false is true. So it doesn't matter what Q. Q can be true or false. The whole argument is true. So we have a tautology, is valid. So what I have here, P of A is false and P of A is true. Therefore, I could be, this 2 implies anything, which is, I call it QA. So I call it 3-4 inconsistency. And so, if I have some example that QA is true and that specific variable is A, I could do generalization now and I say there exists X, QX, which means I'm done. This is my goal. There exists X that make QX true, and we from previously that X we call it A. So what I did, I took 5 and I did existential because I add there exists generalization. Okay.